Okay, so let's do question 4 now. Just a second as I share my screen. Okay. Okay, so this question is Aimosia is a country which has 3 kinds of coins, and they're each worth a different whole number of dollars. And we're also going to assume implicitly that the coins have a positive value, because coins usually do. So Jack, Jill, and Jimmy have at least one of each type of coin. So this is good. It gives us quite a lot of restriction on what their composition of coins can be. Jack has 4 coins, totaling $28. Jill has 5 coins, totaling $21. And Jimmy has exactly 3. What is the total value of Jimmy's coin? So I think from the condition that they each have at least one of each type of coin, it's clear that Jimmy just has one of each type of coin. And so what we're really looking for is the total value of each of the coins summed up. So I'm going to just label these coins because I want to find out about them. If I call them X, Y, and Z, then what I'm looking for in my answer is the value X plus Y plus Z. And I've got a few restrictions on X, Y, and Z. So I know that X, Y, and Z are all different because the question says that they're all a different whole number of dollars. So X, Y, and Z are positive, and X, Y, and Z are whole. And so I think that's all I have about the numbers X, Y, and Z. So now that I've written down all that I know about each of these coins, I can start to work with what they've told me about these people and the coins they have. So Jimmy offers no information. I'm trying to find out about Jimmy. Let's see how we can use Jack and Jill. So I'm going to want to start with Jack. And the reason for that is because Jack has less coins. So the restriction, which says that each of them has at least one of each coin, is a little bit stronger when it comes to Jack than it is when it comes to Jill. And it's stronger because I only have really one scenario for Jack. I know that Jack's money bag has this composition here. I know Jack has one of each at least. And I know that Jack has exactly one of another one, which could be either X, Y, or Z. So that's what I mean. There's only one kind of coin composition that Jack can have. So without loss of generality, I'm going to say that Jack has 2 of the X coin. And this is the only scenario that can happen. So basically we'll log label X the coin that Jack has 2 of. So I think it's really helpful when you're doing these kinds of questions that you turn into pronumerals and you use the pronumerals to represent stuff, to always sort of talk to yourself and qualitatively understand what each of those letters mean. So I've got it really clear in my head now that X is the kind of coin that Jack has 2 of. Okay, so this is pretty much the only scenario for Jack. Now let's look at what it's possible for Jill to have. So there's a few different scenarios based on this. There's a few different scenarios. Jill has 5 coins, right? Jill has 5. So what I definitely know is that so I'm giving a bit of a spoiler, but there's 4 cases altogether. What I definitely know is that in each of these cases, Jill has definitely got at least X, Y, and Z in there. So the first case is where Jill has actually 3 of the same kind of coin that Jack has. So instead of 2 X's, Jill has 3 X's, and that gives Jill 5 coins. Now the second case is where Jill has 2 of the same kind of coin that Jack has 2 of, and 1 of another kind. So let's say Y. That's again log. Because if it was Z instead of Y, that would just be the same case up to relabeling. Now the third case, I've definitely fully done the cases where there are 3 of X and there are 2 of X. There are no other cases that can happen where Jill has 3 of X. And there are no other cases that can happen where Jill has 2 of X. Because when Jill has 2 of X, that leaves 1 coin of a different type. And we already saw that it's the same case if Jill has the Y or the Z. Okay, so this way we can be really sure that we've exhausted all the possibilities where there are 3 X's. We've exhausted all the possibilities where there are 2 X's. And now we're going to look at the possibilities where there are 1 X. Okay, so there are 2 extra coins that we need to fill in these bags with, right? And the 2 distinct cases are if the 2 coins are different from each other. So 1 X and different additional coins. And then there's the case where the coins are the same as each other. So without lots of generality, once again, we're going to say that it's Y. If I did Z instead, it would be the same case up to relabeling. So we're in the case where there's only 1 of the X coin, and then we go into sub cases. So there's one case where the additional coins are different from each other, and then there's the other case where the additional coins are the same as each other. And the reason that I wanted to spell it out like this is so that we can be absolutely sure that we've exhausted all of the different possibilities and we're not missing anything. So 3X is done, 2X is done, and 1X is the last thing. And by splitting it up into cases that are basically opposites of each other, so these cases are complements of each other. If this one is not true, then this has to be true. And if this one is not true, then this has to be true. So by splitting it up into cases like that, I'm definitely sure that I've exhausted all the possibilities and there's nothing left to check. Okay, so now we've got 4 different possibilities and we can probably just, this question keeps on coming up, is this a bash? So bash colloquially can probably mean a really wide array of things. But I think, yeah, in this case, it actually is a bash in the sense that Michael talked about when we were learning about proofs, where there are basically an array of options that you can go through, and you sort of just check each one out. So yeah, I've got these 4 options here, these 4 cases, and I'm gonna start to eliminate some so that I can hone in on the final answer. I feel like everything is a bash. Okay. Amnesia. Anyway, okay, so Summer said for case 3, it cannot be possible since 2x plus y plus z plus, okay, we'll go through that later. And that's definitely how we're going to eliminate case 3. Okay, but I'll just bring everyone's attention to the first 2 cases, just because these are a little quicker. All right, so note that Jack has a total of 28. And so that means that 2x plus y plus z is 28. And then Jill has a total of 21. So in this case, we're saying that 3x plus y plus z is 21. But you'll notice that there are 2 x's here, and the only difference in case 1 is that there are 3 x's. So there's an additional x going from Jack's bag to Jill's bag. And we're saying that this additional x has the effect of taking away 7. But x has to be positive because these are coins. So x equal -7, which is not greater than 0, is a contradiction. And that means it's not case 1. Case 2 goes very similarly. We're saying that there's 2x plus 2y plus z equaling 21. But since the only difference between this case and Jack's bag is the additional y, then that means y is -7. And that's also a contradiction. And then there's case 3, which is a little bit more subtle. So let's see what this means. So in the first 2 cases, it's basically just simultaneous equations, which is a fancy way of saying that we're using 2 pieces of information expressed as equations to get more information, or not more, but we're just using 2 pieces of information. So here we're going to do the exact same thing, but a little more formally, I guess. This is saying that we've got x plus 2y plus 2z equal to 21. So we'll approach this slightly more formally than the other cases. But if I combine Jack and Jill's money bags, which is basically the same as adding these equations to each other, then I've got a total of 3 of the X coin, I've got 3 of the Y coin, and I've got 3 of the Z coin. Oops. Right? Because there's 2 X's here, and then there's 2 Y's and 2 Z's here. So I've got 3 of everything. And since I'm just combining their money bags, it's 21 plus 28, which is 49. Okay, and this is 3 of Jimmy's bag. So it would be really great if this actually gave us our answer by dividing this by 3. That would be amazing. Although it would have been a fake solve because we haven't actually dispelled of this case yet. But anyway, alas, if we try to do that, we'll realize that this case isn't possible because X, Y, and Z are all whole numbers. And so when we divide this by 3, it should be a whole number. However, 49 mod 3 is equal to 1. So that means 49 is not divisible by 3, and X, Y, and Z would not be whole numbers. So since X, Y, and Z are whole, that can't be the case. So case 3 is out of the question. And so we definitely know that it's going to be case 4. And we can start to work on case 4. So let's just zone into case 4. Case 4 is where there's 3 of a different kind to what Jack has 2 of. So from Jack, we've got that 2x plus y plus z, 28. From Jill, we've got that x plus 3 of a kind, different from Jack's, that is 21. Cool. So let's just start to play around with these, because we already know that there's going to be a few possibilities that make this true. There are a few possibilities where x, y, and z are whole numbers, but some of those aren't going to work based on what we know about x, y, and z being different from each other, all different, all positive, all whole. So I think maybe the first thing I want to do is just simplify things a little to zone into what is possible. So I've got x, I've got a z, and I've got a z. So I think probably the simplest thing to do at this point is to subtract Jill from Jack. So we get 7 is equal to x minus 2y. Okay. So let's see, what's one of the possibilities? I've got, maybe I could try y equals to 1. I know that y has to be positive, so 1's a good place to start, which would mean that x would have to be 5, right? And then, well, once x and y have been fixed, then we definitely know how to find z. Z would be we've got 2 times 10 plus y. Wait, sorry, 2 times 5 is what I meant. So 10 plus y plus z is equal to 28, just from using Jack's money bag, which means that z is equal to 17. Wait, no, something's gone wrong. Thank you. I have done something wrong. My bad. So x is not 5. X is 9. Okay. And then from Jack's money bag, we have 18 plus 1 plus z is 28, which means that z would be 9. Okay, so z equal 9. But this is not possible because x is equal to z, and that's not allowed to happen. So that means we can eliminate this case. Y can't be equal to 1. So I guess let's try y equals 2, right? Well, y equals 2 would give us x is equal to 11. And then using Jack's money bag again, we've got z equal to 28 minus 22 minus 2, which is equal to 4. So actually this looks good. They're all positive, they're all different from each other, and they're all whole numbers. This is looking good. And since it's a fake solve contest, you could just give this as the answer. But let's just notice that it's actually not too hard to be absolutely sure that this is the only way it can happen, because there's only one number more that we can check. So if I did y equals 3, I should get a contradiction. And y can't be 4 or greater because that would make x negative, which is not allowed. So let's just really explicitly get rid of this case if we want to be sure, even though this is not necessary for a fake solve. But if this was the case, then x would be equal to 1. And then what would happen? We'd get wait, no. That is not the case, sorry. So x wouldn't go negative, but something else would happen. What if there's a case with a load of cases? What if there's a case with a load of cases with no shortcuts? Okay, I guess this didn't really use any shortcuts, did it? We sort of looked at every single case and got rid of all those possibilities. And then we settled on a number. But yeah, I think I'll just end the solution there. But if you want, you can go ahead and check that this is the only solution. So at some point, I suppose Z will start becoming negative, and then you can stop increasing your values of Y. And then until then, you just have to derive all your contradictions. Okay, any comments and any questions? I'll just highlight the answer. Oh yes, remember to answer the question. So the question would be answered by actually giving the value of Ginny's bag, which is 17. Okay, any questions with that? So just keep in mind also that you didn't have to do exactly this route of checking cases. So I started from Jack because I thought that Jack has the greatest amount of restriction. And I sort of wanted my tree of cases to be like 1, 4. But if I had started with Jill instead, and this 1 is basically to say that there's only one way of expressing what Jack has. And then it branched out into 4 cases. If I had started with Jill instead, well, there would be 2 distinct cases. 2 distinct cases would be X, X, Y, Y, Z, and X, Y, 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 Z. So up to relabeling, these are the only 2 distinct cases. So this would be like Jill 2. And then for each of these, then Jack would have different possibilities, right? So either this would have 2 cases for Jack. Either Jack has one extra of a different one. Oops. Or Jack has 1 extra of the same one that Jill has 3 of. So those are the 2 cases for that. And what are the cases for this? Well, again, up to relabeling, there would be only 2 cases. Either Jack has the other coin extra, or Jack has one of the same ones extra, up to relabeling. So yeah, I don't know why, but I found that it was easier in my head to keep track of this type of case tree than it was to keep track of this kind of case tree, because there was always a risk that I'd forget to check the second case after I worked on these 2. I feel like that's prone to happening in my brain, but yeah, it's a matter of your own preference. But in the end, I guess, yeah, at least for this question, both routes have the same amount to check in the end, because there's 4 total cases, but yeah, like you'll write it down, but there's a risk that you won't remember to come back. So I guess that's why this type of thing is nicer for me. But it's nice to know that there are different options. Okay, any questions?
I guess I can do the comments.
Yeah.
So as for marking scheme, so your marks were awarded. You were awarded 1 mark for identifying the cases, 1 mark for reducing, eliminating the cases, or like finding some sort of contradiction, at least in some of the cases. So like this, and then your final mark was for the final answer. Of course, if you just wrote out the final answer, you'd get full marks as well. Also, this question was, so this question was done pretty much as well as question 3. So out of the, what was it, 2,500 odd people that did the AIMO, 1581. So 1,600 got question 3, 1581 got question 4. So this was also done better than questions 1 and 2. Yeah.
It actually seems like the year 9s did this one better than the year 10s. And the year 10s did worse at this one than they did at question 3.
Oh, yeah.
We could speculate a little bit about that. Maybe when you're older, you'll feel like you should know something that you don't a bit more. Whereas when you're younger, you're a bit more willing to just go with it. A lot of people talking about bashes and cases. I mean, fundamentally, how many cases there are is how difficult a question is. Yeah, that's just sort of a bare bones measure of difficulty. For this question, you can see like at the very beginning, I think Jimmy's value has to be less than 21, right? So it's really just it's a 20 option multiple choice question, and in some sense, that caps the difficulty at eliminating those 20 cases. So you should feel confident about the question when you see something like that, and then it's just a matter of eliminating the cases. I think I did this question a long time ago for another class. I wrote down what my thoughts were at the time, which probably made more sense right after having done the question. Maybe hopefully it'll make sense to you if you've just done the question. I'll put them in the notes. I guess I've left out a lot of the details because I assumed most people were capable of actually filling in some of those details. All right, thank you.